Hello, welcome to today's video. And today I'm going to be looking at the STEP paper 2 from the year 2011. This is going to be question 3 and it's all about trigonometric inequalities and various different properties of these trigonometric functions. So without further ado, let's have a look at what this question is all about. So we'll just put a 3 here. To look at part 1 and A. Before we look at it, let's just have a look at what this statement here is all about. So if we look at it, it says that any function f for which the gradient is greater or equal to 0 is increasing. We may assume this without proof. So what's that saying? So let's just draw a graph quickly just to have a look at what this is saying. So if this is the x-axis. So if we suppose that x1 is less than x2, so let's say this is x1 here, and this is x2 here, then we're looking at f of x1 is going to be less than f of x2. Then we're going to say that it's increasing. That's what this is saying. And if you look at that from what the derivative is doing, if you imagine this line being horizontal to the x-axis, then what it's saying is that the gradient is always greater or equal to 0, then the function is known as increasing. Now, these are all the opportunities that the function can do over this range. So the opportunities, I mean, what I mean to say is that this is what the function can do if it's increasing. All these lines here could be possible gradients for f. So let's have a look. Now we have f of x, concrete case, is equal to sine x subtract x cos x. So, don't really know what this graph looks like. It doesn't really matter. So all we're going to do is try to show that it is increasing. So we're going to use the definition that they give us. If any function f, so this is a function f, is increasing, then this has to be greater than 0. So what we're going to do is we're going to calculate the derivative. But what we're going to do though as well is bear in mind that x is going to be between this range, because that is important to consider. So we'll just put that there, that x be greater or equal to pi by 2. Now, when we calculate this derivative, we should hopefully be able to prove that it's greater than 0, or greater or equal to 0, as it says here. Right, so let's calculate derivative. So that obviously goes to cos x when we differentiate, and then we've got to subtract cos x. And then what we do is we have negative, differentiate the cos x now, so that goes to negative sine x, so that we get x negative sine x, like this. And then we can see that the cos x's cancel out, these two signs change, so that we just get x sine x. Now, how do we know this is greater or equal to 0? Well, if x is in this range, then we can see clearly that x is going to be greater than 0. So then the question is whether sine is greater than 0. Well, if you think about where sine is, then looking at the unit circle, if we just think about it, and then x be the angle here, well, we can see that sine being the opposite over the hypotenuse, we can see that it's always positive. So in other words, it's just the y values up here. So we can see quite clearly then it's greater or equal to 0 from this idea. So how do we say that in words? Well, we can see therefore that f prime of x is greater than 0, and that f prime of 0 is equal to 0. And we can see the graph of sine x is positive. Now, f of x equals sine x is positive. So we can see, therefore, well, I should probably call this g, shouldn't I? Because obviously f is clashing, so notationally, I should just call this thing g. G of x equals sine x is positive. Therefore, we have f is increasing. Good. And we now need to deduce that f of x is greater or equal to 0. So if it's increasing, then if we can show that the minimum value is non-negative, then it will always be above that value. So if imagine this is your value of f at 0, then whenever x2, which is, imagine this is x2, is greater than x1, we're going to have, well, this is clearly non-negative if this is non-negative. So what we're going to do is we're just going to say that in words. So note that f of 0 is equal to 0, because we get sine of 0 is 0, and then obviously cos of x is obviously when x is 0 is 1, but x multiplied with that when x is 0 is going to give you 0, so you have just 0. So that since for all values greater, all values x greater than 0, we have f of x is greater than f of 0, which is equal to 0 in fact. So it's that f of x is greater or equal to, so therefore we have shown what we need to do, which is that f of x is greater or equal to 0, which is what we've got here. F of x is greater or equal to f of 0, which is equal to 0, so therefore we're done. Excellent. So now we're going to move on to part B. So let's have a look through part B before we scroll down too much. In fact, what I might do is just make this a little bit smaller so that we can, oops, I should probably write that x in here, so that's sine x. There we go. Right, so now if we look at part B, yes, this is part all values x, so let's just include that in case we need it. We're going to look at part B. So now we're given this other weird looking expression, well, arc sine. Now, so for those of you who don't know what arc sine is just inverse sine of x. It's another notation. So we've got to show that arc sine of x is greater than x whenever x is greater or equal to greater or equal to 0 and less than 1. So we're given this information that the derivative of, or the differentiating with respect to x, arc sine of x is greater or equal to 1. So what does this mean? Well, now we notice that x is between 0 and 1. Now, I don't really like this d by dx. I mean, what does that tell me? It tells me that the gradient of arc sine is greater or equal to 1. So we know that it's increasing on that range, but it's greater than or equal to 0, which is what we've already been told here. However, I'm not really sure how I will prove this by actually doing the derivative, and indeed step 2 is supposed to be for A level, so we don't actually know how to differentiate inverse trig functions yet. So what we're going to do is we're going to use a very important fact with calculus. If I integrate the derivative from 0 to x, then I get exactly what's inside the function back. In other words, let's just do that. So we integrate from 0 to x, where x is going to be between 0 and 1, otherwise that won't be defined, d by dx, well, let's say be d by dt for the sake of notation, and we're going to do arc sine, of course, arc sine of x, well, it's going to be t, isn't it? So change that. Then this is with respect to t, this is going to be equal to just arc sine of x. This is known as the fundamental theorem of calculus. So, and very useful here, because what we can do is we can integrate both sides here of this inequality and get, therefore, if we integrate this left-hand side, arc sine x will be greater or equal to the integral from 0 to x of 1, which we just write dt. when we do this integral, we'll get that this is greater or equal to x. So the trick here is to spot that if you take a derivative and you integrate it from 0 to x, then that undoes the differentiation, and you actually just end up with the function evaluated at x. And since x is in this range for, make sure we write this, x greater or equal to 0, less than 1, then this will be true. So what we get there is exactly what we want to show. Arc sine x is greater or equal to this, but this is not an inequality here. In fact, this is an equality which will be greater or equal to x, therefore. So what we get is that the integral here will just be x, evaluated at 0. You'll get t evaluated between x and 0, so therefore evaluated at x, if I put this clearly, then we get t evaluated at x and 0, but obviously t at 0 is 0, so we just get x. And that's exactly what we wanted to show. So part C is what we're on to next. Now this looks a little bit harder. So the first parts were really just getting us warmed up into this question, it seems. They weren't particularly hard, but we had to notice something clever about, the expression we're given, and then we can prove it directly. So really, only really one line there, but nonetheless, we're not going to complain about that. So let's have a look at part C. So I'm just going to start part C here, and we can still see the question. So now we're going to let g of x equal x cosec x for whenever x is greater than 0 and less than pi by 2. We need to show that g is increasing and deduce that this weird looking expression, which maybe we might be able to use something from here. I mean, if we can see arc sine x over x maybe, and we've got this g of x. Yes, let's start and see what we get once we've differentiated this, and we'll complete the first part and then see if we can tally up maybe this part with this part, because we can see if we divide this x from both sides, then we can see that this is obviously going to be greater or equal to 1. Maybe somehow we're going to use cosec, I don't know exactly what. But what we're going to do is start. So let's do let g of x be equal to x cosec x. And obviously x is going to be between 0 and pi by 2 strictly. Right, to show increasing, it's exactly the same as part A really, we just differentiate. So what we're going to do is g prime of x, well what we get is we've got x cosec x, so the first one, product rule, you differentiate the x first and leave cosec alone. And so we've got, well I'm going to write that cosec is 1 over sine, and it's always usually a little bit easier when differentiating, integrating and doing things with trigonometric functions, sometimes to write it 1 over sine. Maybe I want to express this as one fraction at the end because I can see I'm going to get something like that. And then what we're going to do is we've got to differentiate this multiplied by x. So what we're going to do is we can differentiate cosec x. Now, if you think about it, it's 1 over sine x, so that's sine x to the power minus 1. And so what we're going to get is we're going to get this expression. So if we differentiate the inside, which will be, if we think this is going to be sine to the minus 1, what we've got to do is bring the power down, bring it down, so that's a negative, and then we're going to have the derivative of this, which is cosine, and that's going to be all over this raised to the power minus 2, which is the same as writing it over cosine squared x. Bring this all together, what we're going to get is we're going to get 1 over sine x subtract cos x over sine squared x. Now, how on earth are we going to tell that this is greater than 0? Well, we're going to have to do some manipulation, clearly. Now, what we do notice is that anything squared is greater than or equal to 0. So if we make this a common denominator and then multiply by a sine, or I've forgotten an x here, but if I multiply this, then what I'm going to get is sine x subtract x cos x over sine squared x. Now, we know the denominator is always greater than equal to 0 because it's a square, perfect square here. It was badly written, let's just make that a little bit neater. So let's see this clearly. Sine squared x, we know that this is greater or equal to 0. Well, in fact, it can't be 0, but we'll notice that we're actually between greater than 0. So if this was 0, we'll be in trouble. So obviously, that's why we have the strict inequality. And so therefore, we can think of just worrying about the numerator, the top part here. So since, let's write that, since sine squared x is greater than 0 for x, obviously greater than 0, and there's also technically between pi by 2, yeah, we get then, so we investigate the top part. Numerator. So, but if we are observant and we remember, we can see that this is nothing but our first expression here, sine x minus x cos x, which is rather nice. It means we don't have to do any work, because we've already shown that this is greater than 0. However, by part A, we have already shown this. Shown this is greater than 0. Excellent, good. So therefore, we're done. We've shown that g prime of x is greater than 0. Now, this is where it gets a little bit more tricky, because what we've got to do now, show that g is increasing, great, and now we have to deduce that this expression here. So this looks a little bit strange. So how on earth are we going to do this, we ask ourselves. So let's have a little think and see if we can come up with a good idea. So let's just write down what we're going to do. So we're on to obviously the second part. So if we look at that, again, we've got to show this expression. So if you remember, we've already shown that this is greater or equal to x. And then we've got this point, this is greater or equal to x cos x. Then we can hopefully think about things that we've been given. If we don't know what to do, then we have to look back to what we've been given. So we know we've got lots of inequalities that we've shown here. So obviously this has got something to do with this maybe, and maybe something to do with what we've been given at the beginning. If we can relate these ideas together, then we are going to do well. So let's just have a think about what we've just shown as well. We've shown that g prime of x is actually, greater than 0, implying that g of x is increasing. Now, if we have shown that, then we could probably just think about what this actually means. So let's just write that down. Since g of x is increasing, we know that if x2 is greater or equal to x1, we have g of x2 is greater or equal to g of x1. Now, so the question we should ask ourselves is, can we find an x2 and an x1? Because we know that g of x is x cos x, so we know that this, so if we let x, if x1 be just x, then we've got our function, which is exactly the right-hand side here. So if we just look at it and stare at it a little bit, we see that g of x is equal to x cos x. So if we think about our x1, if this is going to be true, our x1 is just x. Now we need to find our x2. So when we look back, though, we see that, well, we've got an x here. And we've got that arcsine x is greater or equal to x. So I wonder if we somehow compose g with arcsine x, what we would get. Would we get, indeed, arcsine x over x? Well, let's find out. So if we say, note that g composed with arcsine x is going to be equal to, well, wherever we see an x, we write arcsine x. So we write arcsine x, because we've got x cosec x. So this is g, x, so we write arcsine x here. And then we have to compose it with cosec x. Well, cosec x is just nothing but 1 over sine x. So then we just go through, but 1 over sine. But this is exactly what we want, because arcsine x is the inverse function, meaning it will undo sine and vice versa. So what we get is exactly what we want to show, which is arcsine x here over x. And so we just let x2 be arcsine x, then x2 equals arcsine x, and x1 just be x. Then we have g of x2 is greater or equal to g of x1. So what we get, then g of arcsine x, which is equal to arcsine of x over x, is greater or equal to g of x1, which is equal to x cosec x. Because that's g of x. I should write that maybe. Let's write g of x here. That's what we've stated here. So therefore, that's just x cosec x. So what looked quite hard is actually rather simple when you link the ideas together. So how did I know to do that? Well, it's because we've been constantly proving greater or equal to, and we've got sine as cosec x, and we've got this fact here, f of x2 is greater or equal to f of x1. So I'm immediately thinking, what is my f? This question is always on about showing, something's increasing and showing what that actually means. It means that x2 greater than x1 implies f of x2 greater or equal to x1, f of x1, sorry. So therefore, we have to consider that in the back of our minds all the time. If we do that, we're more likely to solve the problem. You see, the point is that without the guidance, it's quite hard. But with the guidance, it may be easier. So we should always use the guidance. Always look at what you're given. Always look at what you've just proved. Always look at what you've just proved means. We know it's increasing. So we're not going to use that directly because it's not that straightforward, but it will be as straightforward as something else. We just need to make the logical step. So always in step, if you've got three things, you aren't going to show that number 1 is equal to number 2. You're going to try to show that number 1 is equal to number 2, and 2 is equal to 3, so therefore 1 is equal to this third idea. And that's exactly what we do here. So, and as is typical with mathematics, you cannot just compare two things. You have to compare more than two things, and you have to compare them in the right way. So here we have it, exactly that in play. So that is how we solved part C. We're just looking at what we're given and considering how to play around with it. So now we're going to go on to part 2. So this part is obviously going to be harder than part 1 in that we're not given that much now. Look, this is part 1 and we've only just had to improve one sort of slightly hard inequality. Now we've got this sort of weird looking inequality with an x squared, etc., and all of these things here, which really don't seem to, come from much apart from this. If you look here, we've got this step being, similar to this step. I mean, obviously the inequality is the other way around. but then we've got to show considering the function. So we're considering some function, and then here we've got to maybe come up with a function or something to show this inequality. This is a typical idea. So let's have a look. So we've got to prove this exactly here. So let's just write down what we're given. So we write part 2 here. Right, so now we have, suppose that we've got arctan, which is inverse tan of x, the derivative of that is, well, now it's the other way around, isn't it? So it's going to be less than or equal to 1. Less than or equal to 1. And what seems obvious to do is to get rid of this again by the similar guesswork we did here. Helped us more because we've got something that's without this derivative. So we can see therefore from similar argument is integrating the derivative between 0 and x, and noticing that x has to be just greater than or equal to 0. So we can see then we can see that the integral from 0 to x of d by dt again of arctan t dt, which is equal to just arctan x, the fundamental theorem of calculus, and then we get that that's less than or equal to, well, the integral of just 1, which we've already calculated, which is going to be x between 0 and x. So now that we've got this, we've got arctan is less than or equal to x. So now we have to think about how to construct maybe a function to do the job which this part C did. So we constructed this function g of x is equal to x cosec x. So now we can try and construct a similar function maybe to do the job that that function did. So if we look at the question again, it does say to us to consider this function, x inverse tan x. So it does give us something. Here it directly tells us what to do. This, it just tells us to consider this function. So since we've already solved part C, we're going to definitely do what it says and then consider this function. So if we say define g of x to equal this function, they're telling us to consider tan x over x. And if we think about it, if we can show that this function is increasing, since if we put in our inequality here, we get that g of x2 is greater than g of x1, where x2 is just x again, and x2 is, sorry, x1 here will be arctan x, and x2 will be just x. And if we can show that this, when we compose it with arctan x, is exactly going to be, x over arctan x, then maybe we'll be done. So let's just do that. So we're going to do what they say. We're going to consider this function. We're going to compose it with arctan x, because that seems like what we did earlier. We composed g with arcsine x. This time, let's try g with arctan x and see what we've got, and see what pops out. So we're just playing around a little bit at the moment. So if we just see g of arctan x, what we're going to get, obviously, we're going to get tan of arctan x, which will just give us x, because arctan will be undone by the tan. And then at the bottom, we will indeed get arctan x. Now, how does this help us? Well, what we've got here is that this is going to be less than g2 if g is increasing. So since this here is our, if you imagine this being our x1, and then just x being our x2, since this is going to be our tan x over x, we'll get therefore that if we can show g is increasing using what we've been given implicitly. We had to differentiate it to find that arctan x is less than or equal to x. Using this, we'll leave it star. Using star, we note that g2 of x will be greater or equal to g1 of x. So, and letting x1 equal arctan x, and then just obviously x2 will be just x. Just x. Since this is less than this, we get, by definition, g of x1, which is arctan of x, will be, well, that we've already calculated, x arctan x less than or equal to, well, if we just put g of x, which is just tan x over x, tan x over x. Now, just looking at some algebra, we can see that we multiply this inequality, thus x arctan x is greater or equal to tan of x over x, which of course implies that x squared is less than or equal to tan x arctan x. And that is exactly what we need to show. Tan x arctan x is greater or equal to x squared. And we must remember that 0 to pi by 2 is where x lives. So if we just go down for 0 to x to pi by 2, we have to make sure it's a strict inequality, because if we put 0 in here, we would actually indeed get an undefined quantity. So that's why we can see here that it's a strict inequality. Now what we're going to do is we're just going to have to prove one thing though, because we had to say if g is increasing, but we haven't actually proven that. We have no idea whether g is increasing, but we're going to have to prove that. If we prove that though, then we get this inequality and we're done. So what remains to show to prove this fact inequality is that g of x, which is equal to tan of x over x, of course, tan of x over x is increasing. Right, so now we have to differentiate. Therefore, thus g prime of x, well, so what are we going to do? So we've got here quotient rule. So what we're going to do is leave the x alone and differentiate tan there. So that's sec squared x, subtract. We now leave the x alone and then do tan. So we just get tan, and then that's over x squared. So, I mean, we can see that this looks like a load of mess. So how are we going to think about messing this up? So let's see now. So the first thing we should probably think about is that we want to make these into just sines and causes, because we have no idea what these tans and sec squareds are doing. So we're going to think about this as being x over cos squared x And we're going to then multiply through by cos squared x everywhere. So that's easy at the denominator, and obviously here x, then we're going to get x squared cos squared x. But how do we know tan x? Well, tan x sine x over cos x, if we multiply by cos squared x, we can quite clearly see that's just going to cancel with one of these, and we're just going to get sine x cos x. So that's going to be minus sine x cos x. And, well, sine x cos x, if we remember our double sine rule, sorry, sine of 2x I should say, well, that's going to be sine of 2x is 2 sine x cos x. So whenever you see a product of sines and coses, always think to change it maybe to sine 2x. It's easier to integrate or indeed manipulate in general, dealing with one trig function rather than two. So what we're going to do is multiply this everything by 1. Well, we're a clever one. We're going to multiply everything by a 2. And so that's 1, obviously. 2 over 2 is 1. But it looks different, which is what we want. So we've got 2x here, and then it's a 2 sine cos. So we get exactly minus sine 2x by this here. And then this is all over 2x squared cos squared x. Great. Well, the bottom part is positive. Indeed, it's greater than 0 because of our inequality here, which is strict. So therefore, this is no problem. So we can see. So therefore, since 2x squared cos squared x is greater than 0 for x 0 less than x less than pi by 2, we investigate the top. The numerator again, similar from before, only we've had a little less help from them who's set the paper. So what we're going to do is we're going to just consider this 2x subtract sine 2x. We need to show that this is greater than 0. So we're going to call this thing, let's say, what have we got? So we've used that, so let's use h. So letting this be h. Well, so then if we can show that we can see that h of 0, note h of 0 is equal to 0. So if we can show this is increasing again, we're done. So h prime of x is going to equal to, subtract 2 cos 2x. But we notice that this, for x greater than 0, for x greater than 0, h prime is actually greater than 0, because this is a maximum 1, so multiply it by 2, it's a maximum 2, but we're greater than 0, so it's definitely less than 2. So 2 subtract something less than 2 will give you something greater than 0. So what we're going to get, therefore, is that the derivative is greater than 0, and that h is 0. So therefore what we get is that since therefore h is increasing, so we use a lot of increasing functions here, that h is increasing, and so for x, again the same argument, greater than 0, we have h of 0 is less than or equal to h of x, which is equal to 0, of course. This is less than or equal to h of x, which is equal to exactly what we want, which is 2x subtract sine 2x. And this therefore means that the numerator is greater than 0, the denominator is greater than 0, therefore g prime of x is greater, or equal to, well, it's not even equal to, is it? It's greater than 0 because x is never 0. So therefore, g is increasing. And we're done. So a rather tricky part, maybe the last part. The part sort of C here and part 2 were the challenging parts. But once we'd done part C, we just had to come up with some similar ideas, and we had to, think about if this function's increasing, we get that, x2 greater than x1, we get this inequality to prove lots of these inequalities. They just pop out when you use what's given to you in the question. So whenever you're doing STEP, always think what you've written, what does what you've written mean, and always try to use what's given to you. If you do that, then your life will be made a lot easier. So thanks for watching this video, and I'll catch you again soon.